This is lecture 4 of module 1. In this lecture, we will discuss some concepts in nonlinear system analysis, specifically Lyapunov based approach. Reason being that we will use this concept to derive some new training algorithm for neural network based control schemes. Hence, I thought that we must discuss this subject of nonlinear system analysis. You should have some background before you can actually appreciate what we teach in this course. In this course, we will introduce what is nonlinear system, what is linearization, Lyapunov stability theory, some examples. So, what you are seeing is this is our a general state space model, nonlinear system model, x dot equal to f t x u, means it is explicit in time as well as function of x as well as input u. So, this is a state variable model, output is again a nonlinear function h. So, you see x is a vector, f is a vector, y is a vector, so also h is a vector. So, this is a multi input multi output system. When I say this is nonlinear, what does it mean? This is, of course, the first thing that you already know, that linear system means follows principle of superposition, and nonlinear system, it is expected that they are not following principle of superposition. Let me a little for your benefit compare how linear system is different from nonlinear system in terms of superposition principle. This is linear system, nonlinear system. So, here this is my system which is linear. If I give u1, I get y1. So, if I give in this case alpha u1, then also I get here alpha y1. So, same system, say some system G. Now, if I give to same system G another input u2 and I get y2, and finally, the superposition principle is I give alpha 1 u1 plus alpha 2 u2, and at the output I find alpha 1 y1 plus alpha 2 y2. And in nonlinear system, this is just opposite. For example, I give u1, I get y1. So, same system, G nonlinear. When it is a nonlinear system, if I give an input which is alpha 1 u1, I do not, the output is y. So, y is not equal to alpha 1 u1. And similarly, also if same nonlinear system, I provide this to input alpha 1 u1 plus alpha 2 u2, and the output y is not equal to alpha 1 y1 plus alpha 2 y2. So, this is the major difference between a nonlinear system, linear system as far as the difference concerned, but nonlinear system is more than just, it does not follow superposition principle, it has even a broader perspective. much broader perspective, and some of these perspectives are here summarized. That a nonlinear system, we will just discuss that how it has multiple equilibrium point, just shortly we will discuss. It has limit cycles, and if you give a specific sinusoid signal of a specific frequency, then in linear system the output will have the same frequency, whereas nonlinear system may produce subharmonic oscillations or frequencies. Also, its nonlinear system can behave or can exhibit chaos. Chaos means its behavior is highly, steady state behavior is highly unpredictable, random, and multiple modes of behavior also nonlinear system exhibits, that is called bifurcation, one of the example that. Okay. Here this is example of autonomous system, a nonlinear system x dot equal to f x u. Autonomous means it does not explicitly depend on time, and y is h x u. This is a generalized state space model of a nonlinear system which is autonomous. Some systems that have been very widely studied in nonlinear system are known as affine system. They have a specific structure. In our control system design, many times we will discuss this kind of system while designing controller, that is x dot equal to f x plus g x into u. So, this is a nonlinear function, this is another nonlinear function, but you can see that this has a specific structure. And when you have no input, external input, then x dot equal to f x, this is unforced system. What is equilibrium point? Now, at equilibrium point x dot, the dynamics becomes 0, the derivative of the states becomes 0, that is equilibrium point. So, if x e and u e correspond to a specific equilibrium point, you replace and then equate to 0, you find what is equilibrium point. So, what is the linearization? Linearization is a process of replacing the nonlinear system model by its linear counterpart in a small region about its equilibrium point, and we linearize because we have well established tools to analyze and stabilize linear system. So, let us try to understand the basic process of linearization. Let us write the general form of nonlinear system x dot equal to f x u as this written. So, that is we have x 1, x 2, x n, there are n states. So, d x 1 upon d t is f 1 of x 1, x 2 upon x n, and u 1 to u m, we have m input, n output, and so forth. So, this is a generalized way to write, in a very explicit way to write this compact notation x dot equal to f x u. So, f is a vector, you can see f 1, f 2, f n, and let x 1 e, x 2 e, x n e this be a point of equilibrium. Another corresponding the point of equilibrium x e and u e, and where u e is a vector u 1 e, u 2 e, u m e, and x e is x 1 e, x 2 e, x n e. So, we have x e and u e, this two this is an equilibrium point, and this holds true f x e u e is 0, and then we perturb this equilibrium state by allowing x equal to x e plus delta x, little perturbation from x e, similarly little perturbation from u e by delta u. Then Taylor's expansion yields very we can write dx upon dt is f, and this is your x, this is your u due to perturbation, and we expand this using Taylor's expansion. So, you get first this is your equilibrium point, the operating point, and then del f upon del x, you know f is a vector. So, x is also a vector. So, if you differentiate a vector with respect to vector, you get a matrix. So, del f upon del x into delta x, and this matrix is computed at the value x equal to x c, x equal to u e. Similarly, the next term is, these are all first order term, this is the first order term, this is the operating point, the equilibrium point. At equilibrium point, so this del f upon del u, and you compute this again another Jacobian matrix. This is x c, you have to compute at x c and u e and multiply delta u. This is first order expansion plus second order, third order and higher order, but we only go up to first order expansion of Taylor series, because that is where we can apply our linear system theory, because if it goes second order, again the system becomes nonlinear. It is not always true that we can always approximate a nonlinear system around an equilibrium point using first order Taylor series expansion. There is some limit on that. So, let us compute, see what are the this Jacobian matrix del f upon del x. As I said you, this is a matrix. The easiest way to remember is that the first vector in f1 is differentiated with respect to each element of x vector, and that is in the first row. And similarly, in the last row, the last vector of f, this nth vector of f, is differentiated with respect to all the elements of x, and that is the last row. You can easily remember this. So, del f1 by del x1 to del f1 upon del xn. Similarly, del fn upon del x1 to del fn upon to del xn, and these values has to be computed by replacing x as xc. So, x has to be here xc and u has to be ue, and this will be a constant matrix actually. Once you replace xc and ue, this becomes a constant matrix. Similarly, you can compute also del f upon del u, the similar principle. So, obviously, you can see this is a n into n matrix, and this is n rows and m columns. So, n into m matrix this. Okay. So, these are all Jacobian matrices. Let us note here del x upon dx upon dt is dxc upon dt plus d delta x upon dt, because x is xc plus delta e. X is xc plus delta x. So, when I differentiate x with respect to dt, I differentiate xc with respect to dt and delta x with respect to dt. But you can see xc is a equilibrium point, and at that point x dot is 0, derivative is 0. So, this is 0. So, you only get this term d delta x upon dt. Furthermore, f xc ue, this is also 0, because that is how you computed what is xc and ue, okay, by making it 0. So, at equilibrium point x dot, the derivative is 0. Okay. So, now we have already computed in the previous slide, this matrix is actually A matrix and this matrix is B matrix. So, then as we defined, A is del f on del x, B is del f upon del u, and we have neglected the higher order terms. So, we arrive at the linear approximation d delta x upon dt is A delta x plus B delta u. So, this gives sometimes we say also small signal model, that is the behavior of nonlinear system around an equilibrium point, where the dynamics is assumed to be linear, and hence the dynamic is in the linear state space model x dot delta x dot equal to A delta x plus B delta u. Similarly, we had output P outputs, and for P output the functions are h1, h2, hp. In vector notation you can write y equal to h x u. So, Taylor series expansion again we can use y equal to y e plus delta e, that is we perturb our equilibrium point y e with delta y. Then we have the actual system is y equal to h x u. So, using Taylor series we can always write delta y, this delta y is c delta x d delta u, where c and d are again Jacobian matrix computed. So, can you guess now what is this c and what is d? Yes, obviously c is, as we have already said, it has to be del h upon del x. So, you see this has to be P into n matrix, and similarly D is del h upon del u. So, this has to be P into M matrix. So, that is how we linearize also the output y around the equilibrium point y e. So, y e corresponds to x e and u e. So, at value x e u e system response is y e. So, y e is x e, y e is the system response when the input the system state is x e, our system is at equilibrium point. Okay. So, let us take an example. We can see here this is a simple scalar differential equation. X is a scalar, one dimensional, simply one dimensional. So, it is a scalar quantity. So, here it is a scalar differential equation, but nonlinear because of this term x square. You can verify that this equation will not follow the principle of superposition. You linearize it about the origin. You can easily see if I write f x e as 0, then you will find that this is when you make minus x plus x square equal to 0. So, that is minus x plus x square is 0. So, this will lead you x is 0. So, origin, this is an equilibrium point, x is x equal to 0 is an equilibrium point. So, linearize it about origin, you get x dot equal to minus x. its solution is x t equal to x naught e to the power minus t. It is very simple, because this is a simple differential linear differential equation x dot equal to minus x. So, I hope that you are very well aware how to get the solution of this. You can verify now that you put x naught equal to e to the power minus t here, differentiate it, and at x naught when t equal to 0 put this value x naught, you will see that this equation is satisfying. Whatever may be the initial state x naught, the state will settle at x t equal to 0, because whatever initial condition you do, you perturb the system, you perturb the system from its initial position, equilibrium point x naught, it will always come to origin. The state will settle at x t. This is your equilibrium point, which is the only equilibrium point that this linearized system has. So, what we did actually, let me again clarify, we had x dot equal to minus x plus x square. So, first we found out find equilibrium point. So, that is f x c is 0, which is x minus x plus x square. So, x equal to 0 is an equilibrium point. Okay. So, at equilibrium point the linearized equation is, if you follow the our linearization scheme, is minus x, you see, this is your linearized system around the equilibrium point x equal to 0. Okay. And the solution we found out here, x t is x naught e to the power minus t. So, that is the solution to the equilibrium point. Now, if I actually take the exact solution of x t dot, which is minus x plus x square, if I find the actual solution of this nonlinear system, then x t equal to x naught e to the power minus t upon 1 minus x naught plus x naught e to the power minus t. You can try it, an exercise for you. Okay. You can, now this is a simple nonlinear system for which we can find a closed loop solution. Okay. And this is the closed loop solution for this nonlinear system. In general, we cannot express the solution of a nonlinear system in a closed form, but because this is a simple one, we can actually find the closed form solution of this nonlinear system. Okay. So, now the earlier we showed that origin one of the equilibrium point, but there is another equilibrium point, that is when I solve a minus x plus x square is 0, you have x minus 1 is 0, implies x is 0 and x equal to 1. So, there are two equilibrium point actually. So, we talked about linearizing the system around only one equilibrium point x equal to naught, that is 0 origin, whereas there is also another equilibrium point x equal to 1. So, let us see the system behavior around these equilibrium points. So, you say that this is a plot, you can see this is one equilibrium point. What we are showing is this is time axis and this is your x t, we are showing the response, and the value of x t in the beginning t equal to 0, we can start either near to first equilibrium point, that is 0, this particular point, another is 1, this is another equilibrium point. So, if I give initial condition as minus 0.5, you see they all settle minus 0.5, and for plus 0.5, wherever I give here in this zone, they are all going towards 0. Finally, the system at t tends to infinity goes back to the equilibrium point 0. So, that is, if the system is disturbed slightly from its equilibrium point 0, it is near origin, it goes to origin back, it goes back to the origin. Whereas, you look at here, this is a little interesting here, 1, if you go back here, it diverges from 1, very near, it diverges, but surprisingly what happens after it goes to a very high value, comes back and then again goes back to 0. Similarly, you can see this one, this is just before, after 1 it goes and again start from here to here, it jumps and then again goes to 0. Similarly, there is another point here, this is a this particular line, and from here it jumps to here, again goes to 0. So, what you are seeing is that, as I said in the beginning, the equilibrium point 1 is actually an unstable equilibrium point, because from here system diverges from this point, whereas if you start something near origin, if you disturb the system near the equilibrium point origin, which is origin, then it goes back to origin. So, this is so the conclusion is x equal to 0 is a stable equilibrium point, where x equal to 1 is an unstable equilibrium point. We will, at the end of the lecture, we will discuss a little more about this equilibrium points. We will solve 2 examples, but let us discuss some notion of stability in nonlinear system. So, what we talked now is a nonlinear system can be linearized around an equilibrium point. Some equilibrium points are stable equilibrium points, some equilibrium points are unstable equilibrium point. Now, what is concept of stability on nonlinear system? We in linear system we had only one equilibrium point. So, we never talked about locally stable, globally stable, this kind of notion you never heard in linear system, because it has only one equilibrium point. But when it becomes nonlinear system, you always talk about whether it is locally stable, globally stable, all this, because a equilibrium point can be locally stable, also can be globally stable. So, these concepts, as you see that this is not a course on nonlinear system, will not go in details, but whatever minimally necessary will cover in this course. So, x dot equal to f x, this is your say nonlinear system, and the equilibrium point is x bar, this is your equilibrium point. So, equilibrium point x bar is stable in the sense of Lyapunov, this is the definition we are giving now. This whatever in this board what we are seeing, this is all definition. So, we say that x bar is the stable equilibrium point in the sense of Lyapunov if there exists a positive quantity epsilon such that for every delta which is a function of epsilon, we have this particular is satisfied. That is, this is my initial state, that my system state has been disturbed from the equilibrium point x bar. So, there is some disturbance. After you disturb the system, now I am relaxing the system, that is, system dynamically evolves, and after dynamically evolving, where it goes, what happens to the system states. So, if the this disturbance that I have given is less than delta, I cannot infinitely disturb the system and then conclude that system still remains stable, there is. So, I assume some value delta, that is there is a, I put an upper bound by which I give a disturbance to the system. So, if this is true, if this is my disturbance, means this is the way I disturb the system, then x t minus x bar, that is the future state of my system, is not, if x t minus x bar is less than epsilon, then this is stable. What is meaning of that? This, when I say this statement, that if this is my disturbance, finally always my future state minus the equilibrium point, the magnitude, absolute magnitude is always less than epsilon. What does it mean? That is, if I am giving a simple disturbance to the system, the future state do not go far away from the equilibrium point at any point of time. They remain very close to their equilibrium point. So, that is the concept of stability that we define. Then we define a concept of asymptotically stable or asymptotic stability, where this particular difference that we said in the beginning, it is less than epsilon. Now, we are saying if it goes to 0, that is my future state converges to equilibrium point as t tends to infinity, then this is called asymptotically stable. And then we call x bar unstable if it is not stable. If it is neither this nor this, obviously if this is not neither of this, then the system is unstable. So, that these are all definitions we are talking about. So, we defined stability, that is just stable, and then we defined the notion of asymptotic stability. Now, how do we determine it? This notion, whether the system is stable or asymptotically stable. So, we will discuss in this class today two methods. One is indirect method, another is direct method. Indirect method is we linearize the system, that is x dot equal to f x, thus my nonlinear system. Imagine that all we are in the beginning, we are only considering unforced system u equal to 0. So, x dot equal to f x means my u is 0, I have no external force on the system. Now, what I do is that I linearize the system, and this is my, I linearize the system, and that delta x that we wrote earlier, I am again redefining the delta x as again x, just to make our notations very simple. So, here delta x is defined as x, as here. So, now x dot equal to a x plus this g x represents all higher order term, that is second order, third order and so forth. And what is a? Please tell me what is a? A has to be del f upon del x, and this is a n by n matrix. This is my A. Now, g x, which is my higher order term, I assume we say that okay, this higher order term satisfies this condition. You can see that absolute magnitude of g x upon absolute magnitude of x as x tends to 0 is 0. It means that this approximation linearization is valid, first order linearization is using first order Taylor series expansion, this linearization scheme is valid when this higher order term at g x becomes smaller, it becomes very small in comparison to x, then only it can become 0, that is meaning. So, the nonlinear system x dot equal to f x is asymptotically stable if and only if the linear system x dot equal to x is stable. So, this is our theorem or definition, indirect method. So, how to determine, we said that how to determine whether the system is stable or not. So, this is a definition how to determine whether a system is locally stable, stable around an equilibrium point. So, if a system is stable around an equilibrium point, then the linearized system around that equilibrium point, which is x dot equal to a x, all this system, if we analyze the stability of this system, all the eigenvalues of A must be in the left half of the S plane. Okay. All the eigenvalues must be, the real part of the eigenvalues must be negative. The real part of the eigenvalues of A, if they are negative, then the system is asymptotically stable around the equilibrium point. So, that is meaning that all the eigenvalues of A have negative real part. So, what is the advantage of this method? It is very simple, because if x dot equal to f x is given, find out what is x dot equal to A x, that is A is del f upon del x at equilibrium point x equal to x bar or x e, whatever the equilibrium point you say, and then check if A has all the eigenvalues in the whose real parts are all negative. But the problem here is that if eigenvalues, any of these eigenvalues have 0 real part, the real parts are 0, or then that is all, if the eigenvalues are, some of the eigenvalues are on the are imaginary values, then we cannot conclude that the system is locally stable. So, this is, so if some eigenvalues of A are 0, then we cannot draw any conclusion about the stability of nonlinear system. Also, if they have the eigenvalues are simply pure imaginary quantities, they are 0 real part. It is valid only if initial conditions are close to the equilibrium point x bar, because that condition, that higher order term g x upon x, limit x tends to 0, should be 0. So, this is to draw back. So, although this is very simple, now we must look for a very nice method of determining stability, which is known as very popular Lyapunov stability theory, or Lyapunov second, or a direct method. For this x dot equal to f x, we define a Lyapunov function V x with following properties, that this Lyapunov function at origin or at the equilibrium point is 0. This Lyapunov function is a scalar function, this is a scalar function, and the scalar function is always greater than 0 when x is not in the equilibrium point, it is always positive definite. Red derivative of this Lyapunov function is negative definite along the trajectory x dot equal to f x. Then we say the system is stable, then x is asymptotically stable. The method hinges on the existence of Lyapunov function, which is an energy like function. So, we defined a function V x. So, if I want to differentiate V x with respect to dt, so d V x by dt, this is the red derivative. So, then del V by del x into dx by dt. This dx by dt is already my f x, this is my system. So, I replace this f x here. So, dou V by dou x into f x. So, what is my f x now? Because you see V is a scalar function and x is a vector. So, if I expand this, my f x is also a vector. If I expand that, this is a, you can see that this is a dou v by dou x is a row vector and f x is a column vector. So, this is my column vector and this is row vector. Okay. So, if I expand, you can easily see that v dot x dou v by dou x 1 into f 1 plus dou v by dou x 2 plus f 2 and so on dou v by dou x n into f n. So, what is the advantage? This answers stability of nonlinear system without explicitly solving the dynamic equations, can easily handle time varying systems, can determine asymptotic stability as well as plane stability, can determine the region of asymptotic stability or domain of attraction of an equilibrium. We will see all these things through examples. So, here is an example. We take an example, it is a second order system with a cubic nonlinearity, y q is there. If you linearize this system, you get y double dot plus 3 y dot equal to 0. The characteristic equation of linearized system is s into s plus 3. So, you see that you cannot say using the Lyapunov's indirect method system is stable, because one of the pole s is 0. So, indirect method fails here. So, there is a 0 so, we found out y double dot plus 3 y dot is 0, and if I convert this into Laplace domain, s y s square plus s 3 y s is 0. So, if I look at the characteristic polynomial, that is s square plus s into y s is 0. So, my so this is 3 s 3. So, the poles are at s equal to 0, s equal to minus 3. Because one of the pole is at 0, we cannot actually, the indirect method fails in this case. Indirect method fails. So, now we will apply, we saw that indirect method failed, we will apply now the Lyapunov's direct method. So, we had the system which is y double dot plus 3 y plus y q is 0. So, I select the states as x 1 is y and x 2 is y dot. I select these two states and then this equation can be written as a state space format. So, x 1 dot is y dot, which is x 2, and x 2 dot, which is y double dot, is minus 3, this is y dot, sorry. So, y double dot plus 3 y dot. So, minus 3 x 2 minus this is x 1 q. So, this is my state space model. So, for this, okay, the equilibrium point obviously is origin, is the equilibrium point. Now, the Lyapunov function I select for this system V x is 1 upon 4 x 1 to the power 4 plus 1 upon 2 x 2 square. This is like a energy like function. I take the derivative of this. So, V dot x is, I put the formula dou v by dou x 1 x 1 dot dou v by dou x 2 dot, and you can check that x 1 dot is x 2 and x 2 dot is minus 3 x 2 minus x 1 q. So, this is your f 1 and this is your f 2. So, or this is f 1, this is f 2, dou v 1 by dou x 1 f 1 plus dou v by dou x 2 f 2. So, f 1 is x 2 and f 2 is minus 3 x 2 minus x 1 q. So, if you simplify it, v dot x is minus 3 x 2 square. which is always less than 0 because x 2 square other than origin, and when x 2 is not in the origin or x 2 is not 0, it is always negative. So, it follows that the equilibrium point is asymptotically stable, which we could not conclude using indirect method. But what is the disadvantage of the Lyapunov based approach? Although we showed an example where we could not solve or we could not determine the stability using indirect method, we could determine that stability using direct method. There is problem is that there is no systematic way of obtaining Lyapunov function. Rather, finding a Lyapunov function is more of an art than science. So, this is an art, not science, how to find out a Lyapunov function. And Lyapunov stability criterion provides only sufficient condition for stability. So, here just to end the lecture, here are two examples we will solve today. First is to make your concept very clear, how to linearize a system, nonlinear system. So, you can see, because these things we will always encounter in our intelligent control course, and more importantly the Lyapunov stability theory will be used to determine or to derive some new algorithm, training algorithm as well as control algorithm. So, you see here, please note the system dynamics here. Obtain a nonlinear state space representation of this, linearize the system around its equilibrium point. This is your question. So, let us solve it. So, solution. So, we have y double dot equal to 2y minus y square plus 1 dy upon dt plus 1 plus u plus 2 du by dt. This is our the nonlinear dynamics. Now, we have to find the state space model. The state model, first we define the states. So, obviously, let us take x 1 equal to y, just from our experience looking at the form of the structure of this equation, we define x 2 as x 1 dot minus 2 u, which is y dot minus 2 u. This is our definition. So, if with this definition you can write down x 1 dot, which is y dot, and y dot is x 2 plus 2 u. State space means always we write the derivative of the state in terms of other states and input. So, x 1 dot, now here it is a function of x 2 and u in terms of states and u. Similarly, x 2 dot, you can do little algebraic manipulation, and x 2 dot is obviously y double dot minus 2 u dot. And you can see that y double dot minus 2 u dot is this particular quantity. So, we can write that. So, 2 y 2 x 1 minus y is x 1 square plus 1 and dy upon dt, that is x 1 dot is x 2 plus 2 u plus 1, this plus 1 then plus u. So, in simplification this becomes 2 x 1 minus x 1 square plus 1 x 2 plus 2 u plus 1 plus u, it is same. So, actually we did not simplify, it is same. Okay. And finally, your y is x 1. Okay. That is my output. So, how do I linearize it? Set u equal to 0 and x 1 dot equal to 0, so also x 2 dot. So, x 1 dot and x 2 dot both are made 0. If you make that u is 0, so first equation yields x 2 equal to 0 and second equation yields 2 x 1 minus x 1 square plus 1 into x 2 plus 1 is 0. So, solution is x 1 is 1 and x 2 is 0. This is the equilibrium point. So, at this equilibrium point we have to linearize the system. So, linearize around equilibrium point, which is 1 and 0. Apply the formula that we derived earlier using Taylor series expansion, that is delta x dot is del f upon del x at 1 0 delta x जस्ट कट कर दीजिए इसको. So we are not writing here input because u we have assumed to be 0. We are linearizing around the equilibrium point 1 0 and u is 0. So that is the question that is asked to you, delta u. So if you see that, it will be del f by del x. So if you compute that, this, please verify, this will be your this matrix, A matrix, and B matrix is okay. So how do I find it? This simply 0 is del f 1 by del x 1 and f 1 is actually 0 because sorry f 1 is actually del x 2 by del x 1. So by definition this is 0, because similarly this one, the second one is del f 1 by del x 2, sorry del f 1 by del x 2 is this value, that is del x 2 by del x 2. So this is 1. So you are differentiating x 2 with respect to x 2. Like that, please verify this particular solution that we got, and finally delta y is obviously 1 0 delta x. So this is the answer. Now we take the second example. Second example is, we have again a nonlinear system and you are asked to find out whether 1 1 is an equilibrium state, first question. Second is there only, is this the only equilibrium state or there are many, and third is whether the first one, that is given x c, is asymptotically stable. So let us try to solve this equation again, as question is again. So you are given x 1 dot is minus x 1 square solution and x 2 dot minus 2 x 2 square minus x 2 plus x 2 minus x 1 x 2 plus 2. So, the best way is that how do you know that x c 1 1 is an equilibrium point? Just put these values here and see whether they are 0. So, if you put 1 1 here, so this is minus 1 plus 1 which is 0, and in this case when you replace x 2 as 1 and x 1 is 1, again you have minus 2 plus 1 minus 1 plus 2. So, again 0, hence x c is an equilibrium point. So, the first part answer. Second part is whether there are other equilibrium points. The simple way is that to solve it, put x 1 dot 0 x 1 dot equal to 0 and x 2 dot equal to 0 and solve it. You will find these equilibrium points are, so we have more equilibrium point minus 2 by 3 minus 2 by 3, this is one more 0 1 plus root 17 by 4 and 0 1 minus so there are 3 more equilibrium points. You can verify this just putting x 1 dot equal to 0, x 2 dot equal to 0, you will find this solution. The next question was, that is the third part, was that whether if x c is asymptotically stable. So, how do we do it? We linearize the system around x c. So, if you linearize around x c, linearize f x around x c. So, then you get x dot equal to a x, where a is del f upon del x, and please verify a will be minus 1 1 minus 1 minus 4 and the eigenvalues are minus 5 plus or minus root 5 divided by 2. So, you can check that both the eigenvalues has negative real part minus 5, hence it is asymptotically stable. We will continue further discussion on nonlinear system in the next class. For you, here is a little help to follow some reference books. You can follow one of the nice book by Khalil, Nonlinear System, by Prentice Hall. The other one is Slotiner Lee, Applied Nonlinear Control. It's a very nice book. I like this book, Applied Nonlinear Control. Also, M. Vidyasagar has written a nice book, Nonlinear System Analysis, by Prentice Hall. Thank you again.